Time by Percy B. Shelley. Unfathomable sea whose waves are years. Ocean of time whose waters of deep woe are brackish with the salt of human tears. Thou shoreless flood which in thy ebb and flow claspest the limits of mortality, and sick of prey yet howling on for more, vomitest thy wrecks on its inhospitable shore, treacherous in calm and terrible in storm. Who would put forth on thee, unfathomable sea?
A mantra of mainstream politics is the claim that there are no conspiracies, only cock-ups. You especially hear it from journalists who work for the likes of Rupert Murdoch. I wonder why. This mantra is an example of what John Maynard Keynes meant when he said that so-called practical people don't understand their ideas are the legacy of some long-dead philosopher or economist. We're all practical people, aren't we? Aussies are famously practical. But what Keynes is gloating about is that the things that we think in our own minds, that we are convinced are our own precious original thoughts, are more often than not the ideas of some dead philosopher, which a priesthood has programmed us to think, usually by just manipulating our pleasures and pain. Look at conspiracies versus cock-ups. All CEC activists should be familiar with this. This is an idea created by a philosopher 700 years ago. And who was it? William of Cockup, very good. Now, what William of Ockham is famous for is not really an idea, it's a mental sedative known as Occam's razor. It's a dictate to the mind as to how it should function, which states, paraphrase, all things being equal, the simplest explanation is the best. Put another way, KISS, keep it simple, stupid, which is totally interchangeable with keep it stupid, simple, and means the same thing as kiss ass. Keep it simple and stay stupid. What does this mean? Don't look for causes. Don't ask why. Settle for the accepted facts. Don't look for conspiracies. Don't look for the intention behind the action. You see this attitude everywhere. You get it from politicians, from the media, but also from everyday people, like the people at the anti-carbon tax rallies. What do they say? Stop talking about the Queen. Stop talking about genocide. Those aren't the simple explanation. The government just wants to tax us more. Me and my family and my friendly multinational mining company. It's one thing for journalists, for example, to preach this, because they have a vested interest. They are covering for their bosses, who are usually at the centre of the political conspiracies. The real issue is, why do the people accept this line? Think about when we were kids. Kids get pretty smart pretty quick. So if an adult told a kid, don't ask about that, don't wonder about that, don't look into that, what kid would accept it? None. That adult is asking for trouble. So what happens to kids as they grow up to make the majority of the adult population so dumb, so docile and accepting? Through the influence of the culture and our education, we get shaped by philosophies and ideas without even knowing it, as Keynes chortled. He knew because he was a Cambridge apostle, an insider in the conspiracy to suppress the creativity of future generations. In the case of William of Ockham 700 years ago, his razor principle was based on his assertion that truth is unknowable. The ways of God are not open to reason and must be taken on blind faith. Ockham was one of the scholastics, also known as the schoolmen, whom you'll notice Leibniz attacking in his correspondence with Clarke. Also remember from yesterday, Ockham was a dunce, a devotee of John Duns Scotus. But let's follow it through a bit more. If truth is unknowable, what then do we know? We only know what we perceive with our senses. We don't know causes, only effects or outcomes. This is the basis of probability theory. We can't know the causes of events, past or future, but we can compile the statistics describing past events and project that as the probability of future events. Paolo Sarpi, the state theologian of Venice, who was an Ockham acolyte, developed statistical probability as a method to destroy real science. And how did he do it? By studying dice and cards in Venice's casinos. The word casino means little house in Italian. They were a Venetian invention. This is the oldest casino in the world. Casinos and banks were two of Venice's gifts to the world. Wasn't she sweet? In probability theory, causality is reduced to a roll of the dice. It was the perfect tool to suppress the Promethean fire of discovery that so terrified the Venetian oligarchy, the way it terrifies all oligarchies, going all the way back to Zeus and coming all the way up to Prince Philip. Statistical probability is the basis of economics as it is understood today. In the small, that is at the level of the individual, economic causality is reduced to mere seeking pleasure, avoiding pain. All of the individual actions add up to the overall average outcomes, which is what the economists study to make forecasts and policies. This is pure, or should I say impure, Venice. In fact, in Britain it was a Venetian agent following Venice's takeover of Britain in 1688, Bernard de Mandeville, who first enunciated this as the basis of economics in his book, The Fable of the Bees, in which he declared that private vices equals public benefits, or everybody's pursuit of pleasure and avoidance of pain added up to the common good. De Mandeville was a member of the Hellfire Club, which specialised in bestiality, bondage and S&M. To him, pleasure and pain were the same thing, which statistically speaking makes him Mr. Average. The creeps who Anne talked about yesterday, Malthus and Herbert Spencer, took their economic theories from Mandeville. The modern Fabian cult of behavioural economics, which is a rework of Spencer's social Darwinism, has the idea that you achieve economic outcomes by imposing policies that increase pain or pleasure. For example, the carbon tax, which Julia Gillard recently called, quote, the hidden hand. With economics based on statistical probability, it is no surprise then that the entire financial system is one giant casino. Derivatives is all based on probability, as is insurance, another Venetian invention. Credit default swaps are the very worst possible combination, insured derivatives. The very instruments that blew out Lehman Brothers, AIG and the rest of the global financial system in 2008. And none of this is new. From the earliest times that Venetian economics took over England and Holland, those economies suffered gambling-induced financial catastrophes, the tulip bubble and the South Sea bubble, the handiwork of another Venetian agent, John Law. But what's the secret of the casino? The house always wins. Gamblers are as stupid as those who don't want to hear conspiracy theories. They ignore the fact that the people taking their bets aren't gambling, they're making a killing. To play the game, you must willfully blind yourself to reality. Paolo Sarpi, or Father Paul, as his English devotees called him, knew this all too well. He commanded, quote, "Do not follow opinion that wears the title of truth, but rather opinion that wears the title of pleasure or usefulness." To the oligarchy he represented, this willful blindness is what made statistical probability the perfect method to snatch the fire of scientific discovery back from mankind and chain it to the same rock as Prometheus. It kept scientists mesmerised at the roulette table of Zeus's casino. Today, the willful blindness of statistical probability dominates virtually every field of science. You see it in Robert Geller's pronouncement that earthquakes are impossible to predict by statistical methods, so we shouldn't try to make any new discoveries in physical science by which they could be predicted. You see it in the blind faith that global warming alarmists have in the statistical computer models that predict global warming, even after the programmers of those models at East Anglia University are caught conspiring to hide the decline. Talk about the house always wins. You see it in medical science, in the constant citations of how likely you are to contract some horrible disease if you are of a certain age, weight, hair colour, and so on. However, although it may dominate science, it does not advance science and never has. And that is precisely the point. It is not intended to. Gottfried Leibniz, whose extraordinary intellect sparked genuine advancements in many fields of science and industry, including physical economy, fought tirelessly for the principle of necessary and sufficient reason. That truth is knowable to human reason, that nothing happens without a cause that the human mind can discover. The other giants of science we have considered so far this weekend, Pasteur, the Curies and Max Planck, all fearlessly pursued truth. They searched for the cause of natural phenomena because they believed, even as Planck said, had faith that the truth was knowable. And so we come to Albert Einstein. Now, without me saying anything, you already all know that Einstein is a legend. Time magazine named Einstein the man of the 20th century, or the person, sorry, a bit politically correct by the year 2000. We grew up being told that Einstein was the smartest man in the world. Why? Something to do with E equals MC squared, whatever that meant. Unfortunately, this is an example of positivism. We don't know Einstein by his ideas, but by his name and status. But even that's interesting for this reason. The oligarchy despised Einstein. He destroyed Newton in a way that couldn't be denied. As with the vicious attacks on Leibniz, Huygens, later on James Young, and others who made Newton look stupid, Einstein threw them into rug-chewing fits because they couldn't discredit his ideas. Here's another reason they hated Einstein. This is a very famous quote. "Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he does not throw dice." This is usually paraphrased as God doesn't play dice with the universe. You see in this quote that the man acknowledged as the so-called smartest man in the world openly opposed the prevailing axiom of science that there is no causality, only probability. He opposed the central tenet of Sarpi, Bertrand Russell, and the Cambridge Apostles, and the leaders of quantum mechanics. In fact, he more than simply opposed. Einstein was Max Planck's principal ally in the battle to save science from being destroyed by this inhuman fraud. The oligarchy couldn't kill off Einstein, so they tried to muddy the understanding of his ideas, which I suspect included drowning that understanding in a cult of celebrity. Consequently, nowadays Einstein's ideas are presented as logical steps on the same stairway that includes characters such as Newton and Niels Bohr, while the huge controversies and disagreements between them are papered over. Einstein shared his personal outlook of science in a letter to a young student who asked for his advice. Quote, "I want to know how God created this world. I'm not interested in this or that phenomenon, in the spectrum of this or that element. I want to know his thoughts. The rest are details." With this attitude, Einstein got a lot further in the quest to know God's thoughts than most. If he didn't have this attitude, if he didn't think that causality were knowable, but instead that events happen on the mere roll of a dice, the world would have missed out on some amazing discoveries, which we'll look at now. We're going to go into a bit of detail in two areas of Einstein's work. First, quantum physics, and then relativity. The first is the domain of the immeasurably small, while the second relates to both the small and the very large. You'll remember from yesterday's discussion that these are the areas Bernard Riemann directs scientists to go. So keep your thinking caps on. In 1905, the then unknown patent clerk in Switzerland published 4 papers in quick succession in the German physics journal Annalen der Physik. This year was known as Einstein's Annus Mirabilis, or Miracle Year. These papers variously launched quantum physics, proved the existence of atoms, showed that space and time are relative, and launched the nuclear age by formulating E equals mc squared. Because Einstein was an unknown at the time, there was no guarantee he would be published in this peer-reviewed journal. But his papers were previewed by Max Planck, who alone at first recognised the significance of Einstein's revolutionary ideas. Einstein's first paper launched quantum physics by explaining the photoelectric effect. Elisa talked about this earlier. The photoelectric effect is how solar panels work. Now don't go blaming Einstein for the solar power cult. He just explained how it worked. But even with his explanation, it doesn't work well enough to provide baseload power. The photoelectric effect is when light hits a metal plate and it releases electrons. Strangely, the release only occurs in the violet end of the spectrum. Red light, no matter how bright, releases no electrons, but even weak violet light produces electricity. This didn't make sense because under James Clerk Maxwell's laws of electromagnetic radiation, light was understood to be a wave. If light were a wave, then it shouldn't matter what colour it was, because once the metal plate absorbed enough waves, it should have the power required to eject electrons. But this didn't happen. To solve this problem, Einstein applied Max Planck's idea of the quantum. For Planck, the quantum was a conception. Its chief usefulness was in satisfying the equations that describe the distribution of heat across the light spectrum. Remember in the black body problem that Planck solved, as temperatures rose and the colour of heat radiation changed from red to yellow to white, it didn't follow the laws of electromagnetic radiation. Jeans and Rayleigh's calculations had predicted that at higher and higher temperatures, the emitted radiation should have shifted into the ultraviolet range of the spectrum and increased to infinity. In practice, this meant that very high temperatures should emit very high dosages of UV radiation and fry us all, which doesn't happen. Planck was the first to break from the insistence that electromagnetic energy consisted of simple waves, and he conceived of energy as being in little packets, or quantized, as he put it. Calculating the energy this way, he was able to accurately describe the heat distribution. Now, Planck's willingness to consider energy as quanta was revolutionary, but it wasn't enough for him to believe yet that energy as little packets was physically real. And for good reason too. The behaviour of light as a wave had been thoroughly experimentally established, going way back to Huygens, so Planck left it as an open question. And it was Einstein who answered it. To explain the photoelectric effect, Einstein applied Planck's quantum as a physical reality, and Planck's discovery that energy related to frequency expressed as the formula E equals hv. The higher the frequency, the higher the energy. Einstein hypothesized that light consisted of packets of energy, Planck's quanta, which he called photons. An individual photon could only release an electron if it struck the metal with more power than the energy of the electron itself. The energy of a photon is not related to the brightness of the light, because increasing brightness simply means more particles. Rather, power is a function of frequency. The higher the frequency, the greater the power. As Elisa showed, the spectrum of light is produced by differences in the frequency, which go from low frequency at the red end of the spectrum to high frequency at the violet end. If light were a wave, even the higher frequency wave should spread out over the metal and not have enough power in this way. But if light struck the plate as photons, that explained why only the violet end of the spectrum emitted electrons, because that was the high frequency end which possessed the required power. It also explained why electrons could be emitted so quickly under light, because it only requires one photon to occur, not the gradual build-up of wave energy. By this discovery, Einstein turned the 200-year-long wave-particle dispute on its head. He wasn't saying that Newton was right and that Huygens, Young and Fresnel were wrong. He showed it wasn't either or, it was both. Only individual particles of light could produce the photoelectric effect, but those particles had a frequency, which is a property of waves. Einstein explained another experiment similarly. In the experiment, a single electron hitting a metal plate produces an X-ray which strikes another metal plate that then emits a single electron with the same energy as the first. Einstein asked, if the X-ray is only a wave, which indeed it is, how does it know to collapse to the single point on the plate that emits another electron? It had to be both somehow. This is known as the wave-particle paradox, and it's the central problem in quantum physics. The clearest demonstration of this is this famous double-slit experiment. In water, if waves are directed through a barrier with two slits, two sets of waves emerge on the other side which overlap each other. As they overlap, they interfere with each other. In same areas, the two waves combine their force. In some areas, the two waves combine their force to become larger. However, in other places, the two waves cancel each other out. This is known as destructive interference. The points of intersection where the waves cancel each other out create a definite pattern of bands in the overall wave pattern, which you saw in those green lines. Note the double slits at the beginning. These are the two slits in the barrier to start with. So the two sources of waves coming out and expanding. And you can sort of see them, but the lines will show you in a minute. It was replicating this experiment with light in the 19th century that proved that light was a wave. You can see here the effect on a beam of light pass through the double slits, which displays the distinctive bands of destructive interference. That's light this time. But in this experiment, you see something amazing. Individual photons are directed through the double slits one at a time. When they reach a screen, they make a mark. At first, the positions of the marks seem random, but as they build up, you can see the same telltale bands which show destructive wave interference. This proof that the wave of light was made up of packets of energy, quanta, was the beginning of quantum physics. It took science completely out of the visible domain and into the immeasurably small, which opened up a whole new battlefront in the war over scientific method. Quantum physics was applied to the new discoveries of atomic science. Ernest Rutherford's amazing experiment of firing alpha particles through gold foil had produced an amazing effect whereby, although most particles went through, some were deflected and others bounced straight back. This was a shock, which Rutherford compared to firing a cannonball through a tissue paper only to have the cannonball bounce back. It led to a new understanding of atoms. Previously, atoms had been thought of as having a plum pudding arrangement, where the particles, the electrons and the protons, are embedded in a pattern that is fairly evenly distributed. If this were the case, all the alpha particles should have gone straight through, because they were far more massive than any individual electron or proton. So if they hit, they should have knocked them out of the way. So Rutherford conceived of the atom as having most of its mass contained in a tiny nucleus at the centre of the atom, with its electrons arranged around that. This would give the nucleus incredible mass, which made sense of how alpha particles could bounce back after a collision. Instead of a cannonball hitting a tissue paper, it's more like a cannonball hitting a much bigger wrecking ball. The new model of the atom had the equivalent dimensions of someone standing in the middle of the MCG as the nucleus, with cricket balls rolling around high up in the grandstand as the electrons. However, this model of the atom explained the bounce back of alpha particles, but it led to some real quandaries. Take the simplest atom, hydrogen. Hydrogen has one proton and one electron. Now, hopefully your eyes aren't rolling in the back of your heads. But even if they are, this is something you should all know. What's the rule of magnetic attraction? Opposites attract. Remember from yesterday, electrons were discovered to be particles with a negative charge and protons are particles of a positive charge. What does that mean should happen to the electron and proton in the hydrogen atom? They should stick together. If the electron were positioned outside the proton in a stationary position, that should definitely happen, because the only force acting on the electron would be the attraction of the proton. Now we know that doesn't happen because atoms are always so keen to release their electrons. That rules out the positions of the atomic particles being stationary. The theory to explain this was that the electron is in an orbit around the proton, the way planets orbit the sun. The sun's gravity is pulling on the planets, but their orbit keeps them from being pulled in. However, applied to atoms, this led to another problem. For an electron to be in orbit, it needs to maintain an angular acceleration. For example, if the orbit is circular, it would need a constant angular acceleration. But electrons have charge, and it is known that charged particles radiate light when they are accelerating. If this happened to an electron, its radiation of light would cause it to lose its energy, lose its acceleration, and spiral into the nucleus. Niels Bohr, the Danish physicist who was descended from the Venetian sex council to Henry VIII, devised this model of the atom using quanta. Remember from Elisa's class, quanta are discrete packets of energy. Whereas a wave of energy could theoretically be shortened to infinity, Planck's idea of energy as quantized and not as an infinitely divisible wave meant that the quantum was a base packet of energy that couldn't be divided. All energy existed in multiples of this quantum. Bohr borrowed from Planck to say that the quantum of energy determined the distance that an electron orbited around the proton. And there are those numbers you can see. At higher levels of energy, the electron would jump to orbits that were further out. But the distance between the orbits was always the multiple of the quantum. This model was pretty good because it also matched the spectrum lines that showed up in the spectral analysis of hydrogen. And I don't have it in colour, but remember those spectrum lines that Lisa showed, the actual black lines? By this model, they were an exact match. Well, almost an exact match, but that wasn't found till later. So Bohr was pretty pleased with himself. But remember the problem of this model. An orbiting electron would radiate away its energy and spiral into the nucleus. Bohr simply pretended that this doesn't happen. As far as he was concerned, his model made perfect predictions, so why should he be bothered with the paradoxes? The way quantum mechanics is taught, everyone acknowledges Bohr cheated, but they do so admiringly because by the statistical probability method, its outcome agreed with the data, and that's all that mattered. The fact that at its guts, that model is impossible didn't matter. Elisa spoke earlier about the Solvay conferences where all the leading scientists got together to argue about all the new scientific questions opened up by quantum physics. At its heart, the fight was about method. Was reality knowable, as Planck and Einstein insisted, or was it unknowable? And therefore substituted in science by probability, by statistics, as long as the probabilities agreed with the data, as Bohr and his acolytes said. Now, I have to stay here. Before you get the wrong idea, that statistical probability has a definite application, and it often works in that its predictions agree with overall observations. It satisfies the standard for truth in popular science. The scientific method, as taught, is you apply induction to sensory impressions to form a hypothesis, do an experiment to test it, and if the result matches the hypothesis, it's true. But that isn't real science. It is missing something fundamental, which is the why. Real truth is why something happens, the cause. And the answer never lies merely in the effects being observed. Good music is not inspired by the notes of a scale. A good painting is not inspired by the colours of paint. Statistical probability denies that fundamental causality, that intention that shapes the universe and merely maps the effects. It is the abominable idea that 1,000 monkeys playing with 1,000 typewriters could eventually produce a Shakespeare play. Now remember Elisa's story about how good magicians and con artists know it's easier to fool smart adults than children? What followed Bohr was possibly the biggest con job in the history of science, and almost all of these geniuses fell for it to this day, except for real thinkers such as Planck and Einstein. In the early 1920s, one of Planck's followers, a Frenchman named Louis de Broglie, demonstrated the inverse of light waves being particles. He showed that all particles of matter, such as electrons and photons, etc., are waves. Bohr seized on this as an alternative to the unworkable electron orbit model of hydrogen, and he replaced it with a model where the electron is situated outside the nucleus in a standing wave. Now, although de Broglie had demonstrated that particles are waves, he hadn't figured out how to determine the exact position and momentum of the particle at any instant. To him, this was a problem still to be solved. To Bohr, it was a problem to be ignored and only resolved mathematically through statistical probability. This is when quantum physics went nuts and degenerated into quantum mechanics thanks to Bohr's Copenhagen school. Bohr's student, Werner Heisenberg, developed a mathematical formula to calculate the probability of a position of the electron. He based his formula on an assertion that de Broglie's problem of how to determine the position and momentum of a particle was unsolvable. the assertion became known as Heisenberg's uncertainty principle, which states that the more precisely a particle's position is known, the less precisely its momentum will be known, and vice versa. That is, if you know where a particle is, you have no way of knowing where it has come from or where it's going. But if you know where it's going, you will not know where it is. This is a theoretical problem, but it is a close parallel to the physical problem that confronted Johannes Kepler 300 years earlier, when he wrestled with the understanding of why the planets were arranged the way they were and why they moved the way they did. There were 3 statistical models in existence which gave the same appearances: Ptolemy's, Tycho Brahe's and Copernicus's. Just note on this here as it changes, look, compare it to that down there. That's showing that the bodies do not change actual absolute position as the models change, based on all the same models. Kepler demanded to know the why of causality, not the mere what of sense certainty. In school, children are taught about what is called the Copernican revolution because he was the first to say the Earth orbited the Sun, which he actually wasn't. The classical Greeks already knew that. But that was simply a revolution of sense perception. Kepler launched the real revolution of causality. He proposed his vicarious hypothesis. Vicarious means putting yourself in someone else's position, by which instead of trying to understand Mars's orbit from Earth, he imagined himself looking back at the Earth's orbit from Mars. The problem he encountered was that by sticking with the idea that orbits were circular, as in the other 3 models, he couldn't calculate both the longitude and the latitude. The latitude is the position of the planet along its sideways pathway through the sky, measured against the daily pathway of the Sun, which is known as the ecliptic. The longitude is the distance the planet strays above and below that ecliptic line of the Sun. When Kepler calculated the exact longitude, his calculation for latitude was always out. Conversely, when he calculated the exact latitude, his longitude was always out. Not by much, but by enough to be wrong. You can see the similarity between Kepler's problem played out in the large and de Broglie's problem in the very small. So what did Kepler do? Well, who here has heard of the Kepler uncertainty principle? You haven't heard of the Kepler uncertainty principle? Surely, Johannes Kepler, who is barely mentioned in modern textbooks, and so obviously must have been an intellectual dwarf compared to the giants of the 20th century, such as Bohr and Heisenberg, would not have done what Heisenberg declared impossible. Well, he did. Listen to what Einstein wrote about Kepler in the Frankfurter Zeitung on November 9, 1930, in commemoration of the 300th anniversary of Kepler's death. Quote, "In anxious and uncertain times like ours, when it is difficult to find pleasure in humanity and the course of human affairs, it is particularly consoling to think of the serene greatness of a Kepler. Kepler lived in an age in which the reign of law in nature was by no means an accepted certainty. How great must his faith in a uniform law have been, to have given him the strength to devote 10 years of hard and patient work to the empirical investigation of the movement of the planets and the mathematical laws of that movement, entirely on his own, supported by no one and understood by very few. One can never see where a planet really is at any given moment, but only in what direction it can be seen just then from the Earth, which is itself moving in an unknown manner around the Sun. The difficulties thus seemed practically unsurmountable. Kepler had to discover a way of bringing order into this chaos." End quote. What Kepler actually did was throw out the statistical models, and instead of running away from reality, he embraced it. To determine how the planets moved, he went deeper to find out why they moved. Kepler posed the question, what is the mover? This led him to discover gravity nearly 100 years before Newton, who of course didn't discover anything. and to discover that the planets orbited the sun in elliptical orbits that made them speed up as they approached nearer the sun and slow down as they moved further away, but in a lawful way in which they swept out equal areas in equal times. So that was one approach. By comparison, let's look at what Bohr and Heisenberg did. Heisenberg's uncertainty principle meant that, Kepler be damned, the position and momentum of atomic particles can't be known. This was not a statement of scientific fact, but an assertion of a philosophy. To get away with it, in the face of the strident criticisms from Planck, Einstein and their allies, they knew they had to justify it, and they attempted to do so mathematically. Heisenberg developed a mathematical formula that was based on wild assumptions derived from his uncertainty principle. Here are some of them. An electron can shift from one position to another without occupying any space in between. In other words, the electron comes in and out of existence. An individual electron can exist, very briefly, in two different positions at the same time. An electron can travel from here to there along all possible paths simultaneously. Particles can appear out of the nothingness of space, exist for an instant, and then disappear. Scientists call these virtual particles. Compare that idea to the biogenesis-abiogenesis debate of life that Anne and Noel talked about yesterday. What is inexact under Heisenberg's uncertainty principle is existence itself. Or to put it another way, in the very small of quantum mechanics, there is no reality. Or as they'd tell high school students being introduced to this rubbish, quantum mechanics is unreal. Cool, dude. Heisenberg developed his mathematical model of the atom in collaboration with German physicist Max Born. Their model took the form of a matrix, or a series of matrices, which accounted for every probable position of the electron without even attempting to explain physical causality. It was to Max Born that Einstein made his famous statement that God does not play dice with the universe. Quote, "Quantum mechanics is certainly imposing, but an inner voice tells me that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he does not throw dice." To see what is possible mathematically if God does roll dice, have a look at these various mathematical models of the atom for different quantum numbers. All those fuzzy clouds there are the enhanced probabilities of positions of atoms. Electrons, sorry. One of Einstein's friends, Erwin Schrödinger, also took issue with Heisenberg's denial of reality. He challenged it with a thought experiment, which is known famously among physicists as Schrödinger's cat. Imagine a cat inside a sealed box, which also has a flask of poisonous gas. There. Don't tell the RSPCA. And a mechanism to smash the flask, which is triggered by radioactive decay. If an atom decays, the released particle will trigger the mechanism to smash the flask and kill the cat. Schrödinger pointed out that under Heisenberg's model of the atom, in which a particle can exist in two positions at once, which means it can be both decayed and undecayed at the same time, the cat in the box is both alive and dead at the same time. Schrödinger regarded this as an absolutely ridiculous proposition. 3 cheers for Schrödinger. Heisenberg and Born came back at this with some mental gymnastics. They brazenly claimed that inside the box, the cat is both alive and dead at the same time. It is only the act of observation of looking into the box which collapses the two possible quantum states into one. This is now famous as the other aspect of Heisenberg's uncertainty principle, which is that it is not possible to observe anything without changing it. Schrödinger developed his own model of the atom, which he consciously set out to base on reality. His model was based on the wave property of matter, and it worked brilliantly, not just for hydrogen but for all elements. It was a very good effort, which was a tribute to Schrödinger's intention. But it was susceptible to misuse by people in a way he probably wouldn't have approved of, because it was essentially mathematical. Einstein commented on this in a letter to Schrödinger in 1939 when he wrote, quote, "I am as convinced as ever that the statistical wave representation of matter is an incomplete representation of the state of affairs, no matter how practically useful it has proved itself to be." The ringleader of the quantum cult, Niels Bohr, produced what is now accepted as the final word on the wave-particle paradox by merging Schrödinger's wave function with Heisenberg's model to say that the electron is a point particle, but we don't know where it is, and the probability of finding it is given by a wave. So to Bohr, in the double slit experiment, it isn't the light that passes through the slits and interferes with itself, or the electrons that pass through the slits and interferes with itself to determine where it will hit the screen, but the probability that passes through the slits and interferes with itself to determine where the photons land. This is a slower version of what we showed before. I'll keep talking, but you'll see this. This is photons being sent down a tube with two slits in the middle of the tube, one at a time, slowly, and over time, this is what happens. So just watch as I keep reading. Einstein never gave up his opposition to this philosophy. As late in his life as 1950, he again wrote to Schrödinger saying, "You are the only contemporary physicist besides Lauer who sees that one cannot get around the assumption of reality if only one is honest. Most of them simply do not see what sort of risky game they are playing with reality. Reality as something independent of what is experimentally established, i.e., the universal principles hidden to our senses but discernible by our reason." He continued, "It seems to me that the fundamentally statistical character of the theory is simply a consequence of the incompleteness of the description. It is rather rough to see that we are still in the stage of our swaddling clothes, and it is not surprising that the fellows struggle against admitting it, even to themselves." Einstein's argument was that the quantum view of the universe was incomplete. We just don't know enough yet. But we can't jump to the conclusion that since, in reality, we don't know where the particle is, neither does the particle. We can't say that the universe doesn't know where it is. Now let's look at Einstein's ideas on space and time and the question of relativity. I'm going to ask some questions to you in this one, so don't go to sleep. All right, now a superficial look at quantum mechanics might give someone the idea that Einstein proved Newton's views on light to be correct. Well, if that's the way they want to look at it, in the area of relativity, Einstein then turned around and destroyed Newton and revolutionised our conception of the universe. Cast your mind back to yesterday to remember the discussion of Bernhard Riemann. Riemann took issue with the presuppositions of space in Euclidean geometry, which is flat, empty, and linearly extended in all directions. This was the axiom of Newtonian physics. Isaac Newton had insisted that the universe was composed of this flat, empty space, space and time were absolute, and matter was hard balls moving in straight lines, colliding and bouncing off each other. In the Leibniz-Clarke correspondence, Leibniz sent Clarke into a defensive flap by pointing out the absurdities of Newton's idea that space was, as Newton called it, quote, God's sensorium, i.e. the way God senses us all, and consequently that it was absolute, space was absolute and eternal. Leibniz said that if space was God's sense organ for perceiving things, that would mean that the existence of those things did not depend upon God, nor were they created by him. This comeback by Leibniz made Newton and Clarke panic, because espousing the idea of a limited God in those days was dangerous. Now, Newton was actually the follower of a cult known as the Socinians, invented by the Venetians, who rejected the idea of the Trinity. A Socinian had actually been executed in England just a few years before this correspondence. Leibniz knew Newton was a Socinian, and so he had them cold. So for the rest of the correspondence, for those who read it, you see Clarke spend the whole time lamely protesting that when Newton said space was God's sensorium, he didn't mean it. Leibniz's biggest issue with Newton's absolute space and time was that it did not accord with the principle of necessary and sufficient reason. Try and follow this. With the principle being that nothing happens without a reason why it should be so rather than otherwise. If space is empty and absolute, there is no difference between one position in space compared to another. When God created bodies, he would have had no reason to place them in one part of space over another. Because there is a reason for everything God does, said Leibniz, absolute space is not possible. Likewise, if time were absolute, there would be no reason for God to create the world at one moment as opposed to millions of years earlier or later. Another contradiction of God's essential nature. Leibniz said, quote, I hold space to be something merely relative, as time is. That I hold it to be an order of coexistences, as time is an order of successions. For space denotes, in terms of possibility, an order of things which exist at the same time, considered as existing together, without inquiring into their particular manner of existing. And when many things are seen together, one perceives that order of things among themselves. End quote. By this, Leibniz was saying space, time, and matter are all interconnected properties of existence. Thanks to the power of the British Venetian monetarist empire, Newton was worshipped as the high priest of science, whereas Leibniz was viciously slandered and died in abject poverty. So for a time, Newton's conception dominated science until Einstein. Einstein put forward two theories of relativity of time and space, which he called special relativity and general relativity. Before we get onto Einstein's work though, let's look at the idea of relativity generally, as it applies to motion. Now, if your thinking cap has slipped off, quietly put it back on, because we're going to do some thought experiments. And because I have confidence in your intelligence, for most of these I've decided not to use graphics and animation, because Einstein didn't. All up here, because he didn't have them. All right, so let me put some questions to you. All motion is relative to either a fixed point or something else in motion. If you are driving a car on a Macquarie Bank toll road and overtake another car, what direction is that car going relative to you?
Relative to you, it's going backwards.
We all happy with that? Relative to you, that car goes backwards. My 5-year-old daughter points this out to me. What direction are you going? Bam, bam, you're on a Macquarie Bank toll road. You're going backwards too. Okay, back to space and time. If you are going 120 kilometres an hour and the car you overtake is going 100 kilometres an hour, how fast are you going to that car? 20 k's an hour, right? Makes sense so far? This is not Einstein in this part. This is Galilean. This is just almost. Okay. The fastest fast bowlers in cricket can bowl up to 160 kilometres an hour. If Brett Lee, well, all the examples you see in textbooks are baseballers. If Brett Lee is on the back of a very long flatbed truck, travelling at 100 kilometres an hour, and bowled a ball forwards at 160 kilometres an hour, but the ball stays on the truck, how fast would someone on the side of the road with a speed gun clock the speed of the ball? 260 kilometres an hour. What speed would the ball register to someone on the truck? 160. Okay. So all these differences are the examples of relativity. To the person in uniform motion, their actions are normal, but they are different relative to the person at rest. It is a principle of relativity that the principles governing motion apply equally to a stationary object and an object in uniform motion. Still with me? The principle of relativity of motion is that the principles governing motion apply equally. If you're at rest, right, you can do the things you can do at rest, and the way the physical things you do behave. You can pour water, you can juggle balls. You can do those same things if you're in motion, if your motion is uniform. If you're on a plane, you can pour water, you can juggle balls if it's going smoothly. If all of a sudden, someone hits the skids or whatever, then all the laws go out the window, right? But if the motion's uniform, there's no way to tell by the laws of mechanics that you're moving or not, if the motion's uniform. Okay. Now, I think I've warmed you up a bit. There's a few less eyelids shut, which was my objective there. That's good. So keep them open, because I'm going to go through the dimensions of this. I want you to follow on the diagram as I do, all right? Because we want to work out a problem, an arithmetic problem based on motion, because we're setting up another problem by doing it. This is a more complicated example. So this is a large square treadmill that's 4 metres by 4 metres. The treadmill is going that way at 3 metres per second. Now we have a person here and a person here. We have a person at the side and a person at the back. Not on the treadmill yet, right? This person here, we'll call him person A, runs from one side of the treadmill to the other in 1 second. However, the treadmill's moving. So that person cannot run in a straight line, or what would happen?
Go off the edge.
Go off the edge. So he has to go at an angle, right? So if the treadmill is going 3 metres that way, how far does that person actually travel to cross the treadmill?
5 metres.
5 metres, right? With the dimensions of, he's going 4 metres, he's crossed 4 metres in the time that the treadmill's gone 3 metres that way. So for him to do it, he had to go at an angle which defined a hypotenuse, and that's the easiest one to work out, 3, 4, 5. Our guy here was pleased with himself when he got to the other side, right? So he turned around and came back. How long would it take him to get back? 1 second. How far would he travel? 5 metres. Right, so to go up and back takes how long in total? 2 seconds. All right. So, because we just want to compare what he gets to do with what the other guy gets to do. Person B is going this way. In 2 seconds, they're running this way. In 2 seconds, if they go the same speed as person A, how far do they travel? You know what speed he's travelling at? Come on. 5 metres a second. In 2 seconds, how far does he travel? 10 metres. But what happens to the treadmill in those 2 seconds?
It's going backwards 6 metres.
It goes backwards 6 metres. How far has he actually travelled in 2 seconds?
4 metres.
4 metres. So in the time that this guy can go back and across the same distance, this guy can only go across. This guy can go up and back, this guy can only go across once. Now, just bear in mind, the main thing I want to take out of this is not that you remember how to do arithmetic, or that I remember how to do right-angled triangles. It's that these two people confronted with the same dimensions, right, but different physical realities of motion, one can go up and back in the same time as one just goes in one, can go one length. All right, that's the main thing to remember, because this is going to help us understand an actual very famous experiment that took place, which I'll talk about now. Because the laws of mechanics work the same whether you were in uniform motion or stationary. Scientists wondered if the laws of electromagnetism also work the same for moving and stationary objects. In other words, would the speed of light be relative to its motion? Would light emitted from a moving source travel faster than light from a stationary source? Two scientists named Michelson and Morley devised an experiment to test this, which was based on the same principle of the treadmill. And here's how it works. Because they were dealing with the immense speed of light, Michelson and Morley came up with a very novel moving source, which is the rotation of the Earth itself. A beam of light is pointed at a mirror and split into two. So one beam of light goes to that mirror and it's split. One beam goes west, which is what in relation to the rotation of the Earth?
It's
into it. It's like going up the treadmill. It's like where you're supposed to walk on a treadmill, right? The other beam is pointed at a perpendicular angle to the rotation of the Earth. It goes north-south, right? So it's like, one beam, this beam here, is going into the rotation. It's going up the treadmill, and the other beam's going across the treadmill. The treadmill being the Earth, which is spinning. All right? Now, the two beams bounce off separate mirrors and back again to the original mirror, where they recombine, and then they are deflected into this machine here, which is an interferometer. The interferometer tests whether the wavelengths of the recombined beams of light are out of sync and interfere with each other. If the motion of the Earth makes one of those light beams go slower relative to the other, we wouldn't see it, you wouldn't see it with your eyes. The interferometer, though, will be able to check whether the wavelengths are out of sync. Right? The only way they'd be able to sync is if one of the beams of light slows down. And it's not going through a medium. You can look up on the internet the different speed. They've measured how fast light travels through various media. It can really slow down in some, like the slowest is through diamond or something, I think I saw. It's not doing that, right? It's the only thing that might, if it slows down, the only thing that might explain it is the rotation of the Earth, relativity of motion. So this experiment was replicated time and again, over and over again, for 20 years before even Einstein heard about it. And it always produced exactly the same results. Never did the light recombine out of sync. So this was a strange one because it pointed to the speed of light not being relative to motion, but rather some kind of a constant, a sort of cosmic speed limit. And it was against this background that Einstein started thinking about relativity and light. In the Swiss city of Bern, where Einstein worked as a patent clerk, the clock on the town hall was a landmark. A tram ran by the town hall, and it gave Einstein the basis of another thought experiment. He wondered if he was travelling away on the tram from the town hall at the same speed as light, when he looked back at the clock, would the hands on the clock be moving? Think about it. He's on the tram's going away from the town hall, and on the tram you can see the clock, the big clock. He's thinking, if I'm going away at the speed of light and I'm looking back at that clock, would I see the hands on the clock moving?
You'd lose sight of the clock.
All right. Aaron said you'd lose sight of the clock. This is a thought experiment, so think with me. So I heard a broad consensus for no, the hands wouldn't be moving. Anyone disagree with that? Why wouldn't they be moving? Why wouldn't you see them moving?
The light that was reflected from that clock that allowed you to see it is moving at the same speed that you are.
Very good. Right, so the light that allows you to see the action of the clock is moving the same speed as you are, and it never catches you. Right? So, does this mean time stands still? Does this mean time would be standing still?
No. If you're putting time relative to you.
Hang on. If the clock isn't moving, clocks measure what?
Time.
Clocks measure.
Okay, can we agree on this? That in one sense time does appear to be standing still. Would it look like it's standing still? But as Glenn said, if you were carrying a watch with you, or you scratched your nose while you're looking at it, right? Your time is not standing still, right? Well, it's all based on appearances. The appearances of relativity.
And if you went towards the sun,
Time as well.
Well, you should have known that before you got here. I'm trying to show you how Einstein came up to that idea. What I'm saying is, when you've got, there's some relatives with you, time does stand still. Another way Einstein thought about this was to wonder what would happen if he could catch a beam of light. What would it look like? Classical relativity would say that light would appear still, like two cars side by side on a freeway at the same speed. But the Michelson-Morley experiments had found no evidence that light was relative in this way. If light doesn't vary relative to motion, something else must. What's this? Then Einstein thought about a train travelling at the speed of light. So the train passes a stationary observer. Can you all see him in the field there? And at the exact instant, the observer is exactly adjacent to the midpoint of the length of the train. Two simultaneous bolts of lightning strike the train at either end. The observer knows that the lightning bolts are simultaneous because the light from the strikes reaches him at exactly the same time. However, what does a person seated on the train in the very middle see? The light from the strike at the front is moving toward the passenger, while the passenger is moving toward the light. Whereas the light from the strike at the back is moving toward the passenger as the passenger is moving away. How can the strikes be simultaneous to the stationary observer but sequential to the moving passenger? In this experiment, isn't the speed of light behaving in a relative way? But again, based on the Michelson-Morley experiments, Einstein knew that light was a special case. Its speed wasn't relative to whether it were moving or stationary. So he thought about it differently. By examining the very assumptions of the experiment, he posed the question, what do we mean when we say simultaneous? What makes two events simultaneous? Same time. So if the lightning strikes are actually different to the stationary observer and the moving passenger, and light isn't relative, what is it that's different? Position. Go back one step. What does simultaneous mean? Same time. We'll get to that. I just want to make sure we don't jump over this too much.
There can be no events that occur between those two events. There can be no event that occurs after the first and before the second, or after one and before the other.
The relativity between two observers.
The relativity of what? Because it's not the relativity. If that was anything other than light, you'd say, oh, it's the relativity of motion. But they already showed that light didn't follow that. Light is light. The speed of light is the speed of light, whether it's moving or whether it's standing still. Something has to be relative. So what's relative in this situation?
The position of the observer.
No, the position of the observer is the same. The position, you just got an observer, his position's the same. Not his position.
Train, aren't they kind of in the middle of the train, and so when the lightning strikes they would see the other observer, and they can only see it in the light in the peripheral?
All right, listen, just for the sake of time. No, this is good. And we got the rest of the night to play around with it. But we do have 2 presentations this afternoon, so we've got a couple of answers here we have to go with, and I'm going to try and elaborate more. But it's very difficult. The reason that only 1 or 2 have yelled it out is because it's a very difficult idea to wrap your mind around. What's relative or what's different is the time. The time inside the train is going at a different speed than the time outside the train. Einstein said it's the time that is different. Their times are not the same. Now, in the train, time is actually going slower. And they have a word for it, they call it time dilation. Now, I've written here, this was and is a mind-blowing idea which can be hard to accept. So, if some of you feel that, it's fine. I'm sure some of you here are not convinced. However, the amazing thing is Einstein was later proved by experiments to be correct in a measurable way. And I'll give you an example of that. If time actually slows down, a clock should also slow down. Right? If the time... You see, you got... This is mind-blowing because you then think, oh, well, because you're trying to fit it in with your still absolute notion of time in your head. We've all got an absolute notion of time in our head. And when you start learning this, you try and sort of twist it a bit instead of throw it out completely, right? Time is a very relative thing, is what Einstein was saying. So what I'm saying is, it's not just a perception of time that slows down. It's not like you've nearly had an accident and your whole life flashes before your eyes, relativity of time, right? It's actual time slows down. Clocks would also slow down. So let me give you an example of that. Think of a clock. What's this animation? Think of a clock in which the timing mechanism is a beam of light. They animated Einstein to this, good on him. That bounces back and forth. But see the light bouncing between 2 mirrors? Right, see that? When the clock is stationary, the light just bounces in straight lines up and back. But when the clock is in motion, he puts it in a rocket, and he sets the rocket off. Look what the light does. As the light is in motion, as in the case of a treadmill, in order to reach the other side, its trajectory will actually be a diagonal line, and the same as it bounces back. So the trajectory of light in the moving clock is physically longer than the trajectory in a stationary clock. Classical relativity would assume that the light would go faster to keep the same time, but again, that had been proven untrue. It's the time that slows down. This is how they confirmed this experimentally. In 1972, 4 atomic clocks which are the most precise ever invented. They were synchronized with other atomic clocks on Earth. They were put on a US Air Force jet and flown non-stop around the world. When the jet landed, the clocks were compared to the ones they'd been synchronized with, and they were behind in time. They had physically gone slower. They put 4 atomic clocks, the very most accurate ones they could, and that's accuracy is much better than this. Right? These are things that lose like a billionth of a second in a, whatever. They put them on a jet, flew them around the world. Now, they're not going at the speed of light.
In what direction are they going in relation to the rotation? East, west, north, west, east.
North, south.
In this particular example, I'm not sure it mattered. In fact, I'm pretty sure it didn't matter in this particular. This is not. The rotation of the Earth only matters if you're doing that experiment where you're going perpendicular to it. Yeah, it's the relativity to the other clocks, right? So they were going at a high speed is the point. They were going as fast as they could around the world, and when they came back, they were physically slower. That was the experiment. All right. So do not accept everything that I've just told you if you don't want to. That's fine, right? But let's shake things up a bit. The implications of all this were profound. Time wasn't absolute, it was relative. Of course, it is related that space is also relative, which is somewhat easier to understand. For example, how long does it take to get to Sydney?
10 hours.
Kat's first word was the answer. Depends. If you measure distance, if you measure space in action, physical space varies wildly. Measured in time, the distance between Melbourne and Sydney varies wildly according to the mode of action. Over time, weeks became days, became hours, became minutes. I said minutes because I think it's about 60 minutes to Sydney. Measured in time, the whole world is shrinking. The premises of Jules Verne's famous story, Around the World in 80 Days. But what about at the speed of light? If light is a constant, then does that mean that space is absolute at that speed? Well, think about an astronaut who leaves Earth in a rocket that travels at the speed of light. Time goes slower inside that rocket. When that astronaut returns to Earth in, say, a year, he thinks he's only been away for a few days. Consequently, the astronaut and the people on Earth will disagree about how far he has travelled. To the people on Earth, he must have travelled an entire light year. He was away for a year at the speed of light. To him, he thinks that's impossible. He's only travelled as far as light has gone in a few days. That does make you wonder, how big is the universe to light? Still with me? Or are you hating me now? Matter is also not absolute. Don't take this one away from us, you say. For the sake of time, we can't go through it all, but at relativistic speeds, matter would contract. That is, objects physically get shorter, which is known as body dilation. The relativity of time, space, and matter gave Einstein an entirely new conception, which was that these were not separate things, but one interwoven fabric, phenomenon that he compared to a fabric, which he called space-time. LaRouche emphasizes that the matter component should not be ignored, so he uses the term space-time matter, or physical space-time. The relativity of space-time matter led Einstein directly to his famous equation E equals mc squared, which describes how energy and mass are related and gave the world the gift of nuclear power. You could say by this that Einstein was the modern Prometheus. Hang on. There are also many other implications of special relativity that are usually the subject of science fiction, but they shouldn't be completely dismissed. They seem far out because travelling at or faster than the speed of light seems so inconceivable. But who knows what the future holds? One thing you should learn from this weekend is if anyone says to you that is impossible, right, they've got no idea. For example, All right, move on. General relativity now. Einstein himself identified a problem with special relativity, and the problem was the assumption of uniform motion. All these examples of relativity required constant speeds, and in the real world, what motion is perfectly uniform? It's not that special relativity is wrong, but how does it work in the real world? So Einstein started thinking about real-world motion, specifically acceleration. He describes how one day he was thinking about this and he had an idea, he said, that nearly made him fall off his chair. He was thinking about gravity. And when it occurred to him that if a person were in free fall, they wouldn't feel their own weight. From a young age, Einstein had been fascinated by elevators, which were usually open in his day, and they always made him think about relativity, about whether it was the elevator going up or the building going down that was the true motion. When he had this thought about gravity, he applied it to an elevator. What would happen to a person in an elevator if the elevator cables broke and it plummeted to the ground at free fall? What occurred to Einstein is that a person inside the elevator would float for a while.
And then you get shorter.
Conversely, a person in a rocket in space would float, but if that rocket accelerated, that person would fall to the floor just as if they were in a gravitational field. Einstein understood that in free fall, a body accelerates at the same rate of acceleration as the force of the Earth's gravity, which is 9.8. Or who's the old fellow who said 32 feet per second squared? To him, the fact that a person wouldn't feel their own weight when they were in free fall or would float in a free-falling elevator showed him that gravity and acceleration were equivalent. This led Einstein to his idea of general relativity, which finally explained a cause for gravity. For the 200 years that Isaac Newton had been worshipped as the supposed discoverer of gravity, the embarrassing fact that his law couldn't explain its cause, only describe its effects, had to be brushed under the carpet. It had to be accepted that it was a mysterious force that operated across empty space instantaneously. In other words, although it was a measurable force, it wasn't limited by physical reality the way even light had been discovered to be. Initially, this aspect of Newton's law of gravity was ridiculed by leading contemporaries of Newton, such as Huygens, but the priesthood of science operating out of the Royal Society had been able to suppress these objections. Einstein changed that because it wasn't in his nature to accept facts without a cause. So in 1915, Einstein put forward the idea that bodies with mass actually stretched the fabric of space-time. And it was the resulting curvature of the space-time fabric that caused bodies to move, that caused gravity. Now you can picture this idea in a very limited way by thinking of a trampoline on which is placed an old-fashioned medicine ball. The weight of the ball stretches the surface of the trampoline downward, and any smaller ball in the trampoline would be drawn in towards the medicine ball. Or if they were rolled beside the ball, would end up going around it as in an orbit. So you can see this animation of this. Now this animation is obviously limited because it imposes the curvature on an otherwise flat space, but I'm not an animator, so hopefully you get the idea. Now when you think about this in terms of the planets like this, it's very important to remember that nothing is stationary. So the big bodies are also moving, which isn't evident in this animation. The moon is moving around the curvature in space-time caused by the Earth, which is moving around the even larger curvature in space-time caused by the Sun, which itself is moving around the galaxy. Overall, this general relativity idea explains that unlike Newton's idea of a mystical instantaneous force, gravity is caused by the action of the universe. So was Einstein right? Now, although general relativity provided an explanation for gravity, it was another far-out idea, and most scientists rejected it. Einstein was able to point out that his theory explained the anomaly in the orbit of Mercury, which doesn't accord to the predictions of Newtonian physics, which, by the way, takes doing research on a subject like this to discover such a thing that the great Newton's inverse square law, which you were all told explains gravity, describes gravity, it works. Well, no, it doesn't work. It doesn't work for Mercury. Just briefly, as the planets go around the sun in elliptical orbits, they have an effect on each other, which creates variations in the shapes of their orbits. Newton's inverse square law had been considered satisfactory to explain these effects for all the planets except for poor little Mercury. The calculations didn't work. Einstein's space-time curvature, however, did explain it. Einstein proposed another way his theory could be tested using a solar eclipse. If the mass of bodies did actually curve space-time, then light would also curve as it travelled through it. He proposed an experiment in which during a total eclipse, astronomers would take observations of stars in the immediate vicinity of the obscured sun. Now, it's usually impossible to observe anything in the vicinity of the sun, but in the darkness of a total eclipse, stars become visible. Einstein said that when the observed stars from the immediate ring around the sun are compared to their known positions, they would be shown to actually have been the stars that were directly behind the sun's position. In other words, the sun should obscure them. However, they can be seen because the light from those stars bends as it travels around the sun's mass on the way to Earth. It's bent by the sun's mass. And this was a simple idea for an experiment, but in those days it was logistically difficult to do. Total solar eclipses are predictable, but they don't happen every day, and they don't happen everywhere. Different astronomers took up the challenge, and someone should make a movie about this story because it's just unbelievable. One guy travelled to Russia to catch the eclipse there, but he ran smack bang into the Russian Revolution. Others found problems with their equipment, just as they were trying to get set up. There were other cases where the weather was bad, and so they couldn't be seen. One expedition travelled from Europe to the Kimberley in northern WA. This is in the 19-teens. You can imagine the difficulties involved, but that attempt also failed. An American astronomer was the first to do the experiment, and he reported back that Einstein was wrong. But then the problem was his equipment was inaccurate. So these failed experiments began to be reported, and it became like a quest, and it gripped the public's imagination. In 1919, a British astronomer, Sir Arthur Eddington, successfully photographed an eclipse from the West African island of Principe. Because eclipses are easily predictable in advance, Eddington himself had carefully made observations of the stars in that part of the sky 4 months earlier. He had very good at... Can I ask a question here to see you're smart? Why did he do it 4 months earlier?
It'd be night time.
It'd be night time, thank you. The more senior gentleman got it. He had... 4 months earlier, those stars were only there in the night time. Had to be night time. He had very good equipment. His pictures were very clear, and he was able to announce that Einstein's prediction was true. Stars that should have been obscured were indeed visible because their light bent around the sun. And it was this experiment that turned Einstein into the world's most famous scientist and a household name. These observations have been replicated time and again. On the 4th of May this year, NASA scientists announced they had confirmed another one of Einstein's general relativity predictions with an experiment that they had been working on for 47 years. They confirmed that not only does the Earth's mass curve the fabric of space-time, but the Earth's spin actually causes the fabric to twist. Now, because NASA made this announcement with a nice little animated clip, I want to play that so you go and watch it. Okay, so the question is, if it's spinning, if the Earth is spinning with this mass, and there's this space-time fabric, does it twist it as well? Einstein said it would, right? this thing was called Gravity Probe B. They spent 47 years, like I said, working on it. That's why they got. See the twist idea, right? It's twisting. The question was, could they measure that? They had to develop an entirely new technology for everything they did. This is the poor bloke that worked on it from the beginning. But you can imagine, he feels he's just climbed Mount Everest, this guy, right? They had to create the most perfect, ball bearing things, spheres, the most perfect gyroscopic spheres ever made. Gyroscopes create a spin that can provide stability, right? And so they put these things in satellites to go around the Earth, and the satellites had to be constructed in an entirely new way so that as the satellites were close to the atmosphere, there was no drag on the satellite that could have that could interrupt the gyroscope. What they wanted the gyroscope is to be so perfectly spinning in space that any changes that sent the gyroscopes on a slight wobble, these were the ball bearings that they had to manufacture and everything. The slightest changes that would make the gyroscopes wobble instead of spin true would be detected, right? But not be caused by just the mechanics of it. So this is why it took 47 years. And these gyroscopes on this Gravity Probe B measured this actual twist in the curvature. Okay, so what does all this special relativity and general relativity mean for us? Well, let's go back to Bernard Riemann, whose ideas Einstein applied and developed. Remember, Riemann said we must ditch our presuppositions of space as flat and infinitely extended and test all of our so-called facts, in the real physical universe, into the immeasurably small and immeasurably large. Now, in a few minutes, Craig is going to talk about Vernadsky. And Vernadsky, you're going to hear Vernadsky use this term, Riemannian space, in the context of life. That term is going to be impossible to understand if you think of space as what's between you and me now, right? You got to go on a trip with Einstein to have any idea of what Vernadsky is saying when he's saying there's something about the space time of living processes is different than Euclidean space, right? Very important. Because the point about physical space-time is that it is relative and it is both shaped by and shapes the physical action in the universe. Remember from the Leibniz-Clark correspondence, Newton said space was absolute and eternal, which means the universe would be infinite. But that also means there's no final cause or first cause, as Russell's on about, i.e. no creator. Just as Leibniz rejected this, so did Einstein. From Riemann's ideas, Einstein developed the concept that the universe is finite, but it is also unbounded. Einstein said, Riemann's geometry of an n-dimensional space bears the same relation to Euclidean geometry of an n-dimensional space as the general geometry of curved surfaces bears to the geometry of the plane. So in other words, the difference between the two can be understood as the difference between curves and planes, but that's just as an analogy. Einstein used the analogy of a two-dimensional couple existing on a two-dimensional flat plane stretching in all directions to infinity. In that universe, dimensions are the same wherever they are. A single measuring rod would be sufficient to draw squares and circles on any part of the plane that have consistent dimensions wherever they are. But if the two people instead existed on the surface of a sphere, their universe would no longer be infinite. It would be finite, but unbounded. There are no boundaries on a sphere. To discover the finiteness of their universe, Einstein said, our two-dimensional couple would not need to wander over the whole surface of the sphere. Oh, you don't have to go to the far edges of the universe to discover it's finite. All they would need to do is take a sufficiently large area and draw a circle. If they tried to measure the area of the circle, they would soon discover that their previous geometry didn't work. Can anyone tell me why? Curvature. What would be out of shape in a circle on a curve if they're trying to measure the area of it? The radius would be longer than the radius of a flat circle. The ratio of the radius to the circumference is less than pi because the radius of a circle on a sphere is longer than the radius on a flat plane. From this, they would be able to figure out they were on a sphere and that their universe wasn't infinite. But Einstein warned, echoing Riemann, that the couple would need to consider a sufficiently large area. If they just took a small area, the differences wouldn't be noticeable, and they would assume their universe was flat and infinite. The definite curvature of space that Einstein proved through general relativity means that the universe is finite. However, it isn't limited, it isn't bounded. The universe is constantly progressing, constantly changing to higher and higher levels of development. The upward progression that we see in the biosphere, which Anne covered yesterday, is mirrored in the progression in the state of the universe as a whole. Creation is ongoing, and new physical states are constantly being created. Stephen Hawking doesn't think so because he bases his view of the universe on the second law of thermodynamics. So he believes it's all going to go into time reversal one day and collapse, and he also believes it's shaped like a pea. The universe, the real universe of Einstein, is also mirrored in the upward progression of human society, which is the basis of Lyndon LaRouche's science of physical economy. Human beings change the universe by their creativity. We willfully create new states of space-time matter. Each new human discovery adds a new dimensionality to the universe, which Riemann described as a continuous manifold which progresses from a state denoted as n to n plus 1, n plus 2, n plus 3, n plus 4, and so on. Each new plus 1 addition, a new dimensionality created by human discovery. As civilization has progressed from hunter-gatherer societies to fishing culture, agrarian, to industrial, the universe has transformed. Not just our perspective of it, but in actuality. There is no limit to this progress because the universe is unbounded. A recent point made by Lyndon LaRouche is that our potential is not just to create new physical states, but also new principles, which Elisa asked him about yesterday. He has pointed to the trajectory of energy progress we should be on, wherein we should already be moving from nuclear fission to fusion and then on to matter-antimatter reactions. With the enormous energy flux densities promised by those levels of technology, our power over space-time matter will give us abilities now considered inconceivable. Don't doubt it. How could a hunter-gatherer have ever conceived of now simple actions such as using a microwave oven? As we conquer space with the application of these higher energy flux density technologies, we'll have an ability to accelerate at constant 1g, which will soon have us going at speeds approaching relativistic levels, i.e., approaching the speed of light. What principles we will be creating by doing actions in the universe that the universe doesn't do itself, or does through us. The fact that we can even think about such possibilities owes a great deal to Einstein's life and work. Einstein deserves to be remembered for his commitment to truth, driven by his belief that everything has a cause which is capable of being understood by human reason. Such a commitment requires courage. In the book, The Path of the Pole, the story is told of Einstein being asked how he had been able to make so many profound discoveries. Smiling in understanding, Einstein replied, by challenging an axiom. Remember, the axioms Einstein challenged carried the weight of the high priest of science, Isaac Newton. Most people don't challenge axioms and therefore don't make discoveries, and so come to accept the line that you can't. To challenge axioms is a willful act of true courage, which requires placing your identity outside of yourself and letting go of the security of sense perception. Einstein thought deeply about these matters. Listen to what he wrote to a rabbi who had asked for his advice in consoling his 19-year-old daughter because her 16-year-old sister, whom the rabbi described as a, quote, sinless, beautiful child, had suddenly died. This sort of letter was not uncommon for Einstein, whom many people wrote to for advice because he had this reputation as the smartest man in the world. Einstein replied this way, quote, "A human being is a part of the whole, called by us universe, a part limited in time and space. He experiences himself, his thoughts and feelings as something separated from the rest, a kind of optical delusion of his consciousness. This delusion is a kind of prison for us, restricting us to our personal desires and to affection for a few persons nearest to us. Our task must be to free ourselves from this prison by widening our circle of compassion to embrace all living creatures and the whole nature in its beauty. Nobody is able to achieve this completely, but the striving for such achievement is in itself a part of the liberation and a foundation for inner security." On another occasion, Einstein wrote, quote, "The true value of a human being is determined primarily by the measure and sense in which he has attained liberation from self." Einstein devoted his whole life to developing a unified field theory, a kind of explanation for everything. He never lost his belief that human reason could perceive causes. He didn't achieve a unified field theory, just as he never resolved the mysteries of quantum physics. But he didn't give up. He wrote, "Nobody who has really gone deeply into the matter will deny that in practice the world of phenomena uniquely determines the theoretical system, in spite of the fact that there is no logical bridge between phenomena and their theoretical principles. This is what Leibniz describes so happily as a pre-established harmony." What Einstein hated about quantum mechanics was that it denied Leibniz's pre-established harmony. It asserted that at its very smallest level, the universe is irrational, a warped foundation for science and philosophy and knowledge today. Driven by his firm belief in pre-established harmony, even when Einstein didn't realise his goals, he opened the door to the solutions. For example, in a few minutes when Craig talks about Vernadsky and Vernadsky's thoughts on the space-time of living processes, Vernadsky advanced profound ideas about living processes which were directly influenced by the concepts of Einstein and Riemann. In turn, the LaRouche Youth Movement's basement science team have recently identified that the key to understanding quantum physics in a lawful way lies in the study of biological processes as developed by Vernadsky. I'll give you two quick examples. Photosynthesis, which is the power station for living processes, is extraordinarily efficient in converting the sun's rays into energy. To the mechanical mind infected by the second law of thermodynamics, the efficiency is mind-blowing. Our power stations, at best, are only about 50% efficient. Photosynthesis is almost 100%. To get anywhere near the near-perfect efficiency of photosynthesis, scientists have to use superconductors at extremely low temperatures, but plants do it at air temperature. We know that whatever is allowing this to occur is happening at a quantum level. The other example involves both quantum physics and space-time. A recent discovery showed life exerting power at a quantum level on the spin of electrons. Nolene's talked yesterday about polarized light. Electrons' spin is a quantum property analogous to the polarization of light. In an experiment, when DNA strands, i.e. living DNA strands, were deposited on a piece of gold, the electrons emitted when UV light was shone on the plate had a shockingly high level of spin alignment. To achieve these levels abiotically would require magnetic fields hundreds of times stronger than an MRI machine, yet it occurs under the influence of light at normal room temperature. Einstein would be excited about the possibility that biological science, conducting investigations of the space-time of life, could unravel the mysteries of the quantum physics. As he said, logic will take you from A to B, imagination will take you everywhere. Thank you.